All right, what we want to talk about today are simply examples of solids that we can encounter at kind of normal temperatures and pressures, say here on Earth or anywhere in the universe where we would have normal temperature and pressures. When I say normal temperature and pressures, I'm talking about around 0 degrees Celsius, plus or minus 100 degrees, maybe even up to temperatures of maybe 500, 600 degrees. Regular pressures, like our atmospheric pressure, 101.3 kilopascals, and again, maybe down to 50 kilopascals, maybe 40 or 30, not close to zero, like not outer space pressures, because then matter starts to behave differently when you get to extremes. When you get to very low pressures, even solids will vaporize, so you get funny things happening to stuff that we would normally expect at regular temperatures and pressures. Same with super high pressures. You get to 500 times the pressure of our atmosphere, pressures that are existing in the interior of planets maybe, or in the interior of the sun. Then you've got much different things happening to atoms and molecules. Molecules aren't even existing, they're just completely squeezed out of existence. And same with high temperatures. If we're talking about the interior of the sun, we're talking about millions and millions of degrees Kelvin, and electrons aren't even existing in orbits anymore at those temperatures. The electrons are off doing whatever they want to do. There's nuclei hanging around there. They're even being squeezed together into other nuclei fusion. So we're not talking about those extremes. We're just talking about regular temperatures and pressures and regular matter that we would encounter in a laboratory in everyday life. And we want to break it down into the different types of material that we know. And we're going to start off with ionic solids. And like I said yesterday at the beginning, last year when we looked at intermolecular forces, we started by talking about ion-ion interactions. I didn't include that in yesterday's discussion because we were going to deal with that today. So ionic solids, we're really talking about ion-ion interactions. They're strong, full charged ions attracting to each other. Now another change that I've made from the past is I quickly went online, grabbed a bunch of pictures that represent these different types of solids so that we can make some annotations on here instead of me trying to draw it on the board, which is always really scary. So these are just some pictures, and I know that photocopying didn't work that great, and my printout actually didn't work that great, but it's not bad. What's that? No, I won't even bother with it. As I think about it, it wasn't as useful. It's not that big of a deal. Yeah. I can discuss that as we go, right? It wasn't worth the time. We actually included ionic bonding in the intermolecular forces last year. We would have called them ion-ion forces. In this case, we're kind of separating it out. We're saying that if you've got ions that are attracted to each other, it will form an ionic solid. And we're saying then that ionic bonding is stronger than all of the other intermolecular forces, H bonding, dipole-dipole, London forces. It doesn't really matter whether we include it as an intermolecular force or not, as long as we know that we have to categorize it somewhere, and that ionic bonding is stronger. A couple little annotations I want to add to this. Once you're done, you guys are still right away here. At the end of the lesson, I'm going to put a bunch of different compounds up, and I'm going to ask you to classify what type of intermolecular forces hold these things together, what type of, bonding is holding it together, and the answer for some of them will obviously be ionic bonding. In order for you to identify that, you can always default back to that thing that they tell you back in grade 9, that an ionic bond is formed, and you can put this down below or off to the side, but it's formed by, right, a metal ion, a metal. Right? Remember the metals, and the way we logic this out is that metals off to the left have a very low ionization energy, right? They've got a low ionization energy, and it's a metal and a nonmetal. And the property of the nonmetal is that it has a high electron affinity, right? And that results in that complete transfer of the electron. Remember back to our grade 11 lessons. These guys down here, they have a very weak pull on their outer electron. It's because their nuclear charge is small, their atoms tend to be large, their electrons are far away from the nucleus, so they give up that electron easily, and the nonmetals have high nuclear charges. They'll attract that electron to it greatly, and it'll result in the transfer of an electron. So when we've got our metal, nonmetal, we have an ionic solid, all right? Another important aspect that's going to come across in all of these solids that we talk about today are the bonds and whether they're directional or not, all right? Directional bonds simply mean that they can apply forces on their neighboring atoms in certain directions, not kind of forces wherever, like in any direction, but a very specific direction, much like scaffolding, all right? Let me show you some examples here. Nothing to write down here. This is on your page already. If we talk about something like sodium chloride, like we always talk about when we talk about ionic compounds, when you put sodium chloride formula units together, you get this repeating sodium chloride, sodium chloride, sodium chloride, and the force of attraction exists between those, and you have very much attraction in between these two. So those are attracted together. Those are attracted together. We actually have repulsion existing between the diagonal molecules. So in here, we actually have repulsion. What that means is you can't pull them apart, but you can't take that square and just push it over. You know what I mean? You can't just push the square over, because it's like there's a bar that exists between these two that holds them apart. That's just like actual scaffolding. Does everybody know what scaffolding is? You see scaffolding sometimes. You usually see it on the outside of the VPP because they're always working on that place. Anyway, you see the scaffolding, and what will happen is they'll have bars, right, between joints. But if you just had those bars, if you pushed at it from this end, you could actually flatten that thing out. It would just pivot around all these points and just kind of squish out. So they put a support bar in there that keeps it from falling over like that. And they'll put another support bar in there. Usually there's a pin in here, and it keeps you from pushing that square right over. That's exactly what happens in a lattice structure like this. You have attraction, attraction, attraction. It keeps the corners of the square together, but these actually repel each other. So if you try to push on the edge of the square, it doesn't go anywhere. It's just like scaffolding. So it's a very strong structure. Here, this is on your sheet. There, I don't know if you can see, it's very tiny on your sheet. Sodium chloride, and there's that repeating sodium chloride, and that's a particular type of lattice structure. This sheet here, and I know the picture's not great because it's faded on the left, but what I wanted you to just see here by giving you this graphic is that there are many different types of repeating structures. Sodium chloride is the simplest. It's called a center-faced cubic structure. It means that it's made up of a main cube, which then has ions or objects, could be molecules, but in this case, ions in the center of that particular cubic structure, all right? You can take entire courses at university just studying the crystal structure of various solids. This thing that I'm going to teach you in a day, probably 2 days if it takes me a little bit longer, about solids and their crystals that they form, you can do entire careers studying crystals, all right? Mrs. Murray, she has a geology background, which means she would have taken courses on various types of minerals, and she would have studied the crystal structure of each of those minerals, all right? And the crystal structure, the microscopic crystal structure, when it is expanded on by more and more ions, results in what we see as the actual crystals. So this is like salt under a microscope. And the really neat thing about it is the microscopic crystal structure gets reflected in what we actually see when we look at a crystal that has grown to a larger size. So this cube that makes up a little salt crystal is actually a reflection of what is happening on an ion by ion basis in that particular crystal, okay? Now you'll notice here, these are all represented as cubes, and that's because when crystallographers, when people who study crystals, when they try to categorize what type of crystal structure it is, they have what they call the unit cell or the unit cube. But you'll notice this is much more angular than this, which means when this crystal grows, you're going to get a different shape of crystal out of it when it continues to grow. Here you can see there's almost it's not a cube, but it's almost like a pentagon in this area, which then has like a diamond on this shape. And when that grows, when this particular crystal grows, this is what is this, fluorite, calcium fluoride, you'll have a different shaped crystal than a cube in the end, because it's going to be a reflection of what those ions are doing. All right, so there's just some little extra information on crystallography. The essence that I need you to know is the ion-ion interaction is strong. The ion-ion interaction is directional, specific directions for the forces, and therefore ionic crystals are very hard. They have very high melting points and boiling points because of the strength of this crystal, all right? So there's some other crystals there, nothing to write down here. We've looked at some crystals, so let's write down some properties. Again, we've written these properties before. We did it last year when we talked about ion-ion interactions. We talked about ionic solids when we first did our bonding, would have been Unit 2 back in grade 11. We have you write down the properties of ionic compounds every time. Hard but brittle. It means you cannot take a piece of salt in between your thumb and your finger and squeeze it. It will not deform. You could take a piece of wax in between your thumb and finger and squeeze it, and you will win. The wax will become flattened. You take a piece of salt between your thumb and finger and squeeze it, you will lose. Your finger will just, your skin will just deform to around the shape of the salt crystal. But if you were to take it between, say, 2 spoons or a knife and a spoon or a mortar and pestle, you can break those structures. Just like if the wind blows hard enough, scaffolding will come down. It'll take a large force, but when it does come down, it'll come down catastrophically. Everything will come apart. Conduct electricity in the liquid state or when in solution but not in the solid state. We've talked about this in grade 11. Put it in the liquid state, melt it. You now have mobile ions. Put it in solution, the ions go freely. Again, you have mobile ions, they conduct. In the solid state, the ions are locked into place, no conducting. And they have high melting points, and that's simply a reflection of that directional force, all right, the directional bonds. It's just information, so it shouldn't take much. If you've got any questions on that, I think it's pretty straightforward. Okay, so this is new, all right? Now we want to talk about metallic crystals. And we have not talked about metals as solids at all. Not throughout any of your science careers. So this is new information for you. Metals exist as crystals. If you have a hunk of copper, there is a regular repeating lattice structure, just like the ionic, of copper atoms. They're not ions, they're atoms. So when you have a hunk of copper, you have a lattice structure of copper atoms. If you have gold, you have repeating gold atoms. If you have a hunk of sodium, you have repeating sodium atoms. If you have an alloy where you've mixed two metals together, you'll have some ratio of, and then let's say you're making brass, which I think is zinc and copper, you'll have a ratio of zinc atoms to copper atoms. But they're just atoms. Well, they're not exactly atoms. That's what we want to talk about. So the question is, how is a crystal of metal different than an ionic solid, all right, or different than ice, which is also a solid? And that's what we want to talk about. The important thing is here is that the metals have low ionization energy, so they have loosely held electrons, and they all have low ionization energies. It's not that we're putting a metal with a nonmetal, where the nonmetal is going to grab up that loose electron. We're putting a metal atom beside another metal atom, and they're both going to not want that electron. So there's really not a strong attraction for the outer electron by any of the atoms in the structure. So all of the atoms really don't care that much about the valence electrons. They do not form ionic bonds with themselves. They also have a very low delta En. This is just some pictures of various things we're going to talk about. We just finished talking about ionic, and we're just into metallic crystals. If you're dealing with a pure metal, the delta En is 0. So it's not like there's an attraction of the electrons towards any of the nuclei. If you have an alloy, there will be a slight delta En in between those differing atoms, but it will also be small. So what we have here is, this last statement, they don't have enough valence electrons to form covalent bonds with each other. So what we have here are atoms that are side by side that have really no attraction for their valence electrons. The outer shell electrons, and in the case of most of these guys, remember those d electrons are a little closer. So these outer electrons, and maybe some of these, if we're talking about these guys, these outer electrons are very loosely held. So how do we explain then properties of metallic crystals if we've got all these atoms in a row and they really have no attraction for their outer electrons? The theory that we use is something called the electron C model. Don't worry about that. Don't worry about that. And because this is new, I have to have you write it all down because it really is, a new idea for you. It's about 2 slides, and I'm going to just put it up there and let you write. And then we'll talk about what is meant by the electron C model. let me take your arcs. Look at what's happened to this. If I had moved it earlier on, it's beautiful. It's a Christmas scene. Trying to triangulate that buzz, but I wasn't paying enough attention. There was some sound reflection coming off the wall there, so I thought it was here, but getting indications. Anyway, I don't shut the thing off. Anyway, all right. Always more entertaining when it's in a backpack, because then it sounds like a little cow in the backpack. That's funny. How are we doing? We're getting there. The rest of the crowd is getting restless. We need to keep going to maintain control. The Christmas season is coming, you know. You guys are getting restless. I need to keep throwing information at you. What? They canceled your picture? How the heck does that happen?
They're running behind and they're missing lights, so they're like not working. Then they just told me to reschedule.
For like next week sometime? And you went to effort to present yourself in a presentable fashion. Jeepers. Gotta keep going. We're losing Shauna here. So I've got to put on a better show to come 9 o'clock to keep you awake. Whew. I'll have to think about that. Yep. Mm-hmm. Yes, that's right. Yep. I'll get to that in a second, just because of the ordering of things, but that's correct. Yep. Okay, I'd like to go back to the first slide and just read it over with you and make some sense out of it, and then we'll go to the picture and I'll apply what what we've been talking about here, and hopefully we can make some sense out of it. So, the electron C model pictures metals as being composed of a 3D densely packed core of metallic cations, which means they're implying that they've lost those valence electrons within a delocalized region of shared mobile valence electrons. All right, that's exciting. There's some great chemistry words in there. Now, pictures metals as being composed of a 3D densely packed core of metallic cations. So let's imagine we're talking about some, well, my example on the page is gold, and I'm going to flip to the next slide in a moment, and we'll use that picture. You don't have to draw this picture here, but I just want to kind of draw something a little more detailed than what you have there. So what it's saying is, if you then have a gold atom, and you put it up against another gold atom, and it doesn't matter which metals we're talking about, I'm just using gold because that's on my little picture here. What we're saying is their valence electrons are so weakly held that if we were to draw the valence orbit for this, so let's say we put a little nuclei in here, and we've got some other orbits on the inside, and we're going to just draw them as Bohr orbits just for the sake of being a little easier. Actually, no, you can think of them as being s orbitals. Let's think of them as being s orbitals. We won't worry about p orbitals or d orbitals, just for the sake of ease. And so these orbitals are where those inner electrons are most likely going to be found. And then you've got the outer s orbital. And what's happening is it is going to be so large because it's in the next orbit that those outer s orbitals will overlap. Okay? So what's that mean? If you had two of them, you might think of it as kind of a covalent bond. But it's not a regular covalent bond as we might think, because they're not really being attracted into this space because they're so loosely held. So what that produces is a region, right? So if we were to add these two up, just like we did for hydrogen, they would add together to make this orbital. And so what we would have is this region, right, of space in here where the valence electrons, that's really hard to see, so I'll put it in a different color. The valence electrons are kind of hanging out. So they've overlapped. They're orbitals. The orbitals can add, just like we do when we make a bond, like a sigma bond. And it gives this larger region where the valence electrons can kind of roam around and hang out. Because remember, in orbitals, we don't have specific places for them to be. They just exist in that space, and they kind of move around in such a way that they are in that space. If we add another atom to this pair of atoms, the same thing is going to happen. We're going to have the inner electrons, but then we're going to have its outer shell overlap with the other overlap. And as I continue this representation, we have overlap of the valence shells. How many circles did I want there? And in the end, this is three-dimensional. All of these overlapping valence shells, where the electrons are very weakly held, they form a great big giant bond. All right? In a molecule like water, the bond is only in the space around the atoms, which means the poor electrons that exist in these orbitals are locked in place. We say that something like a sigma bond or a pi bond is a localized bond. Localized means it cannot move beyond its local region. A bond that's made up like this of all of these outer shells that are overlapping, results in what we call a delocalized bond. It's as if it creates one massive bond where the valence electrons from all of the atoms can exist. All right? In the movie on resonance structures, I would have used the term delocalized bond. I would have drawn a picture of maybe carbonate, and it would have had a resonant structure that looked like this, right? You guys, some of you had to draw carbonate on the assignment. And what that is that that double bond, the pi bond, gets spread over 3 locations, and that is also a delocalized bond. But it's a very small delocalized bond. It means that the pi bond, the 2 electrons in the pi bond, can exist anywhere over top of the carbon, bouncing back and forth around between the oxygens. So that's a delocalized bond because it goes beyond just a localized bond, which can only exist between 2 nuclei, okay? But this delocalized bond is really a baby delocalized bond compared to the delocalized bond that exists in a metallic structure. In a metallic structure, we have 3-dimensional, right? We have 3-dimensional, where the delocalized bond exists throughout the structure. From one end of a hunk of metal to the other end of a hunk of metal.
Excuse me, Mr. Sanders. I need Sarah Cecile to gather her things, please. She'll be signing out.
Okay, no problem.
Thank you.
From one end of a metallic piece of metal to the other end of the piece of metal is one giant bond that extends from one end to the other that electrons can actually flow through at will. They kind of bounce around between the nuclei, all right? So here's the way we consider it. If we've got this delocalized bond, which exists, and we've got these valence electrons that are really not attracted to any nuclei, that electron might be moving in a direction where it leaves the region of its own nucleus, wanders close to the neighbor's nucleus, and now is actually more attracted to the neighbor's nucleus. This process can happen constantly. It wanders maybe into this region of space, is now part of this nucleus, and this atom wanders into this region of space, is now part of this atom, wanders back into this region of space, is now part of this atom. So what we have is, if all of the electrons are really kind of not stuck, the valence electrons, to the nucleus, why don't we just consider the nucleus as being the cation? It has lost control of its electrons. So let's consider it as being made up of a bunch of cations, which then has this big bond that spreads from one end of the hunk of the metal to the other. And the electrons, those valence electrons that were part of that atom, can wander from nuclei to nuclei. The overall structure is neutral because the total charge on all the cations plus the total charge on all those wandering electrons equals 0 because they cancel each other out. So the overall structure is neutral, but those electrons are able to just kind of move from one atom to the other. Now, what does that mean? How is this being held together? The glue for a structure like this is the attraction of the wandering electrons with the closest nuclei, because they're going to be electrostatically attracted to each other because they're oppositely charged. So if you were to take a snapshot, if you could, kind of like our hydrogen game for acids and bases, if you could have the electrons roaming around and then say, stop, everybody stop, or take a picture, click, take a picture, what would happen is, if you could locate the electrons, which we know you can't because of the Heisenberg uncertainty principle, but if you could, you would always have electrons that are evenly spread out, that are attracting to the nearest, and the weaker attraction would go over there, there'd be a weak attraction over there, would be attracted to the nearest nuclei. And then if you said, go, start wandering again, because those outer electrons, they're not attracted to those nuclei very much because they're way far away, they're in this delocalized bond, they would move around past each other, and if you said, stop, and then you looked again, you would see the electrons in different locations, but again, they'd be near to some of the nuclei and they would cause a force of attraction. So those wandering electrons kind of hold the whole pack together, okay? Now, this type of attraction is not directional. This type of attraction is not like scaffolding. Scaffolding has spot there, no moving around, repulsion, attraction, it is strong. This is non-directional. It means that when you take a snapshot, wherever that electron happens to be, there might be a strong force of attraction to this one because it's close, and a weak force of attraction to that one because it's far, a little weaker to that one, and a little weaker to that one. It's non-directional. The attractions are everywhere, all right? So the forces holding them together are kind of loosey-goosey, I would say. They're kind of like, whoa, oh, you know, we're kind of barely being held together, okay? So that results in non-directional forces. The valence shells of metals are closer to being empty due to the low ionization energy. The electrons are able to move freely between the nuclei of the atoms. These electrons occupy the spaces between the positive nuclei, and this space is really essentially one giant bond, all right? Covalent means two things are sharing, right? There's sharing of electrons, but it's not covalent. It's, I don't even know how to describe it, communal, right? They're communal electrons. Remember how I used to describe the large atoms as being, you know, the delinquent parents of the atom world? You know, where's your electron there, francium? Yeah, I have no idea where my outer electron is. I really don't care. You know, this could have been taken away years ago. I might be positive I don't even know it, right? And now we can take that and we can expand it. If you had then a whole bunch of cesium or francium, it doesn't become like a bunch of delinquent parents. It literally becomes a commune, all right? So you got cesium. Cesium, do you know where your electron is? I don't know. It's probably living 2 doors down. I really don't care, you know, where it sleeps. You know, it's like a bunch of hippies in a commune. You know, I don't know. My electron, I haven't seen it in years. It was here at one point, but it might be on the other side of the crystal structure. I really don't care. There's another electron around. It might be my neighbor's electron, but hey, I'll take care of that electron. I don't care, right? So now it doesn't become like, you know, like the delinquent parent, but like a commune. The electrons can kind of go wherever they go. All right. So they can exist in that space. Okay. The force of attraction between the positively charged cations and the sea of mobile electrons is called a metallic bond. So this great big, you know, orbital, this great big thing, and this force of attraction we call a metallic bond. And a metallic bond is non-directional, as the electrons are attracted to more than two nuclei. So they're non-directional. It means that there's no scaffolding here. It's all held together by, you know, by just attractions all over the place. Now, let's talk a little bit about properties of ones that deal with this. Now, one thing that I do want to do, I'm looking at my sheet and I'm attempting to figure out what do I want you to add to this sheet. And what I'd like you to write underneath here on your page. And again, I'm kind of tripping over this because I just made this page, but what I want you to write are the important things that I mentioned even about the ionic, and we'll go and add it to the ionic. The question that I want to, or the important things that you want to get out of this stuff is whether the bond is a localized bond, all right? I'll write it down. And whether the forces are directional or not, because that really tells you all of the properties. So underneath here, what I'd like you to put now, to kind of summarize all this stuff that we've been talking about, a metallic bond, so a metallic bond, all right, is non-localized. Non-localized, by the way, for electrons means they can go wherever they want within the bond. It's got lots of space. So if you want to define that, you can. The electrons are free to move wherever. That's what non-localized means. And the bonds are non-directional, which means the forces of attraction are kind of anywhere and everywhere. Going back to the ionic bond, how would we describe the localization of the attraction or of the bonds? They're localized. They're stuck together, very close. So we have localized bond. It means the electrons are not free to move everywhere. They're stuck in the ions. They don't have options to move around. The electrons are stuck in the ions. So ionic bonds are localized, and how else would you describe them if we're looking at our two things? They're directional. I'm going to add one more thing. Localized electrons. All right? Localized electrons. Non-localized electrons. Okay? Now let's talk about how this translates into some properties. If you've got, and here we've got our positive ions, and then the dots just represent, and the little negative marks just represent the electrons, right? And what we're saying here is, in a metallic bond, these electrons are free to move wherever. It'll always be balanced. If an electron is moving left in one region of the metal, another electron somewhere else will be moving right. And if an electron's moving up in one piece of the metal, another electron will be moving down. That's regular neutral metal. And that's the way the electrons move. Now in B, this picture represents the fact that if I had an electrical charge on the end of the metal, those little pictures that I've added are kind of like representing charges. Remember when you used to do electricity, you would talk about a negative charge and a positive charge, right? You see what I mean? Remember that little cell? So what I'm saying is, if I took some electrodes and I put it on the ends of a piece of metal, and this side was negative and this side was positive, because the valence electrons are able to just kind of bounce around and aren't attracted necessarily strongly to the nuclei, then those valence electrons, and we've got them drawn in this picture, and I'm not a fan of this picture, they actually would do a little bounce around dance that would result in the electrons slowly moving to the right. They've got them drawn as straight lines, right? They've got it drawn as if the electrons would just fly right down the middle of the channels there and would go right to the end. If that were the case, that piece of metal would have no resistance. And I am talking a little bit of physics here, right? But if the electrons could flow right in the middle of the rows of ions without being impeded, there would be no resistance whatsoever. But in reality, what's happening is the electrons are bouncing off of various nuclei, and so it results in a chaotic dance of the electrons bouncing around. But you'll notice there's now a net kind of travel towards the positive charge. So when it's not, when it's not being affected by charges, the electrons meander around in all directions. But when you put electric charges on it, they will be attracted to that end. This represents the conductivity of metals. Metals are conductive because their non-localized electrons are able to move freely in one direction from one end of the crystal to the other. So, ionic compounds will conduct in liquid form because their ions can freely move. Metals conduct in solid form because their delocalized electrons can freely move. Heat. Heat, and then this one here, if we apply a force to it, it bends. This is malleability or ductility. In other words, this is indicating that it's malleable or ductile. If you've got bonds that are delocalized, if you take a piece of metal and you hammer it hard enough, all you're going to do is shift the nuclei around. But because the bond itself spreads over the whole thing, the piece of metal isn't going to just break. An ionic solid, if you hammer it hard enough, because it's directional, it fractures and breaks. But a metallic bond, if you hammer it hard enough, all it does is shift the nuclei. But because the bond is delocalized, it just makes the bond bend around the corner and still holds the bulk material together. So you can take a piece of metal and you can bend it, and all you're doing is deforming that bond, but it doesn't let go because it's not directional. So you can change the direction of the bonds. You can manipulate the position of the nuclei, and that bond will just manipulate and stretch. So because it's a non-directional bond, you can hammer it really thin and it stays together. It just squeezes the delocalized attracted bond, just squeezes it thin. Or you can bend it, or you can do all kinds of things. So because of this, again, non-directional bond, you can bend the metal. You apply heat to it, because the atom is not locked into place, it's able to wiggle around in that delocalized bond, and so it can vibrate like crazy because it's not locked into place. That'll cause the neighbor to vibrate and the other neighbor to vibrate, and you will conduct heat down it very quickly. So again, the non-directional bond results in it being a good heat conductor. And that's why ionic compounds are not good conductors of heat. They are locked into place. They hardly vibrate when heat is added to it. So we'll finish off by the looks of it for today, talking about the properties of metallic. I might just start into covalent network, but I'm not going to get it finished. Actually, no, I still got to do small molecules. So I am going to need Monday. By the looks of it, I'm going to need all of Monday to finish this discussion, which is fine. What's that? Yeah, and I've got a little extra on my pictures now, so I'm going to talk a little more about that and that, a little more detail. But yeah, that'll work. It's good. Did I stop at metallic last day? Last time I did it? Yeah. Maybe I'll stop there here as well, which is fine. So they're good electrical conductors. The electrons can move freely through the metallic structure. They can move from one ion to the next. Malleable and ductile. As the metal is bent, the sea of electrons is able to move, exerting force of attraction on the cations. So even though you try to bend it or squeeze it into a wire, shape of a wire, that's ductility, or you try to hammer it thin, that sea of electrons holds it together. Now you might think that if you've got this delocalized structure and it seems to be kind of non-directional, kind of willy-nilly here, if you're going to melt the stuff, you might think it might be really easy to just kind of pull these ions out of their lattice structure and have them melt and move and flow like a liquid. But due to the size of this delocalized bond and due to the number of little attractive forces that each electron can exert, it's actually a fairly robust structure. It holds together really well. So metals have high melting points and high boiling points because that electron sea attraction, I got one more slide here, I think it's one more. That electron sea is stronger, yep, that's the last one. We'll stop there. That electron sea is very strong in holding it together. Ionic solids have high melting points and boiling points because of the strength of their directional forces. Metallic bonds have high melting points and boiling points due to the, adaptability of that sea of electrons to hang on to its positive nuclei. It's the sea of electrons that's holding everything together. Oh, interesting. I got metallic or melting point increases across the period and decreases as you go down the group. So decrease as you go down the group might indicate that the larger valence shells then have a weaker ability to hold those ions into place. I guess so. Guess that kind of makes sense. Never thought about it that way. Increases as you go across the period. As you go across the period, the nuclear charge increases and the forces on those nuclei are a little greater. That makes sense to me. That could follow the same trend as ionization energy, straight up. Okay, so that's where we will end, and we will finish off. We've got to talk about two more types of crystals, as you can see on the page. Small molecule molecular solids, which is basically things like ice. And then we've got something called covalent network solids, which is, again, something new that you've not heard of. And the timing will work well.